Hello, everyone. Welcome to this session. For today, we are going to learn about priority queues and binary heaps. So, in our previous discussions, we talked about different kinds of trees, such as general trees, binary trees, and binary search trees. So, for today, we are going to discuss about PQ and binary heaps as to how it actually implements or uses the three algorithms. So when we talk about priority queue, this one is actually a special kind of or special type of a queue. So which is if you have already taken data structures and algorithm, I believe so. You have already discussed, you have already learned about the idea of queue, which is a first in, first out algorithm. So yeah, PQ is a special type of queue, which elements are or which elements are associated with a priority value. So, and these elements can be served on the basis of their priority. That is, the higher priority elements are most likely the elements that are going to be served first. So, however, there are instances that if an element or an elements are with the same priority value, or if there are occurrence of same priority, there are they are going to be served as um, according to their order. No, so just like what happened in a bank queuing system. So considering that we have already a number queuing system, and there are actually lanes there that are intended for the senior citizens or the people with disability. So though we have already the queuing order as a regular citizen, so if ever there are citizens that are belong to that now, like senior citizen or PWD, they are going to be served first. So they will be catered first. So that's where priority queue comes in. So that's why a system or that our system will be able to will be able to cater that kind of situation. Okay, so uh, basically, when we talk about queue, it's about first in, first out. When we talk about PQ, it's on the basis of priority. Okay, and the highest priority is the uh, the re- that is the element that is going to be removed first. So priority queues are are used to efficiently support finding the item with the highest priority across the series of operations. So the order of the queuing will be changed if there are situations like the uh, there are there are elements that are needed to be served first on top of the other. Okay, so the some operations of the or basic operations of the queue are insert. So it is used to add elements to a queue, and then there is also this find, which is used to search or retrieve data from a queue, and then we also have delete, which is used to remove data from our priority. Okay, so the most common applications of priority queues are the in terms of the operating system design, there is this what we call resource allocation. So priority queues are used for that allocation in terms of the resources, like for an instance, assigning memory to a certain application that is running currently. Another example is a gateway calls for Skype, for Gmeet, or for MS Teams. Okay, we also have, I guess, another example for that is assigning employees to a certain project. No, so the, the the project manager could actually select the best employees to to be assigned on a certain project, and that's what we call priority. Okay, Another is it could be budgeting, no? In terms of budgeting money for certain project. Okay, so what are the what should be the project that is given highest priority in terms of allocating budget? Okay, so another is data compression. So in computer science, there is this what we call Huffman coding or Huffman algorithm that is actually most common in data compression. So when we talk about this algorithm or that Huffman algorithm, this is actually an a way to efficiently, it's an efficient method of data compression without using the without using much or without actually using information, without, I mean, without losing information. So when you compress the data into a from a bigger size into a smaller size, which is that's the use of, that's actually the role of data compression without losing data, and that's where that's actually happening in coding. Okay, another is the discrete event simulation. So when we talk about this application, this would refer to an insertion of like time tagging guest or time tagging events rather, the which time represents the priority of an event, and then the lowest time means it is probably the highest priority. Okay, so now let's talk about the implementation. The priority queue can be implemented through arrays, okay, which is a fixed base data structure, or a structure which is fixed. Okay, and then we have also a linked list. It is a structure that is a dynamic type of structure, and then we also have here binary heap, which is most commonly priority queue is implemented through binary heap. And then we can also implement priority queue in using binary search tree. Okay, so our for our for this topic, we are going to implement priority queue using arrays and in the representation of binary heap. Okay, so we have here the representation in variants. So the structure of a, a priority queue should be a complete binary tree. So recall that complete binary tree is it's a binary tree having all children with at least one child, okay, in which all the levels are completely filled except possibly the lowest node. Okay, so that's it. So that's complete binary tree. So meaning to say, the all the nodes in the tree should be completely filled from left to right in level order. Okay, so that's the structure of priority queue. So it must be a complete binary tree. Okay. Now, when we talk about the another rule or another property of a priority queue, a it should follow the heap order property. So what is this heap order property? It depends on what we are going to achieve. We have actually two types, the min heap and then the max heap. Now when we talk about min heap, this min heap property of a priority queue or min heap property of a binary heap, this is a binary tree where all the parents must be less than or equal to its children. So therefore, the root is the lowest value has the lowest value among all other nodes or on its children. Now, in the contrary, max heap is the parent must be greater than or equal to its children. So therefore, the root is greater than or equal to every other. So this is an example of max heap where all the nodes are. So as you can see here, rather, I mean, it's as you can see here in our binary tree, we have here a root 93, a root node which is 93, and all its and the left child and the right child of this node is actually less than to this parent node, so which are 87 and 42 respectively. So unlike binary search tree, you have to follow the property in which all the nodes in the left on the left subtree should be less than to the root node, and the root node should be less than the right node or the right subtree. So in binary heap or in max heap, if you're gonna be using max heap, the node should be the root or the parent node should be greater than to its children. So as you can see here, you have 93, it's greater than the children, 87 and 42. So if you try to also look at it on the other side, so you have the 87 as a parent node is has two children, 32 and 66, and it's also greater than its children. So the same with 32, which are having children like 28 and 19, which is also greater than its children. The same with 66 and of course 42. So that's it. No. Okay. So it depends on what you would like to achieve. Again, it's either max hip or min hip. Now, let's have this max hip algorithm. So in max hip algorithm, by the way, in performing the operations of max hip and min hip, you could follow there are actually a lot of books that does different from what we are going to do right now. I mean, anyway, I'm going to show you the two implementations of max heap. So basically the binary heap uses a an array. No, it's a representation of an array because it would be easier for for this algorithm to use or implement arrays in terms of the managing data. Why is it? Uh, it's because of the time complexity. Okay, so which we actually talked that one in data structures and algorithm. So in terms of in the insertion, it could be or it could be a constant value of one or up to zero of n or to zero of log n. Okay, but in terms of finding a value, it is actually constant value. Okay, so because we use a certain formula. So the formulas are this one. So if you're going to use that array, because there are other implementations that the array for storing the elements of this algorithm is it does not include, or it's actually omit what they call this one, and skip nila ang zero, and then they are going to start with one. If in the event na we follow this algorithm that we use the array based on zero. So this is the formula that we should follow. So we have here to look for the parent, we are going to use the formula I minus 1 divided by 2, where I is actually your index. So okay, right here, you have here the index. So these are your index, okay, and then these are your elements. All right, and index or is. Okay, so using the formula to find a parent, again you use the I minus 1 divided by 2, and for looking or for finding the left child, you will use 2I plus 1, where I is the index, and for right child, you will need to use the formula 2I plus 2. If again you are using array based on 0. So let's try. Um, of course, if we have already created a binary heap of binary heap in this priority queue implementation, we could easily look for the parent of 87 and uh, 42, and also the same way with looking for the child of 87, looking for the child of 66, and even looking for the child of 32. So if since of course this is only just a representation. Okay, so we'll have to use formula as again, we'll have to use formula for that, and these are the formulas that we are going to follow. So right here, let's say for an instance, if we are going to look for the parent of, let's say, 26. Okay, so let's look for the parent of 26. So we use the formula I minus 1 divided by 2. So the value of the value of the index value of our 26 is actually 5. So using the formula, you substitute the value of 5 minus 1 divided by 2, which is actually 2, all right? Because 5 minus 1 is 4, and then when you divide it by 2, the result is 2. Now, as you can see, the parent of 26, yan, the parent of 26 is actually the element which has index of 2. Okay? If you try to look at in the binary heap, you have here the parent of 26 is actually 40. Okay? As easy as that. You can actually look, you can, there's a, I mean, in terms of finding the parent or finding for the parent of uh, certain node, it is constant value. So kung sa data structures of algorithm pa ni is, it's 0 of 1 time complexity. All right, so let's have another example. Let's say parent of um, 30. As we all know, the parent of 30 is actually this one, 66, right? In our binary heap representation. So, however, to do it like in a program, we'll need to follow the formula, which is the I value of, let's say the I value of, or the index value of 30 is actually, what is it? 10, okay? So you will need to substitute this 10 in the formula, 10 minus 1 divided by 2. So that is 10 minus 1, 9, okay? 9 divided by 2. So since index is an int base, we assume, yeah, of course, it is an int base. It is always an int base. There's no index in a double or float representation. So we have here 9 divided by 2 is actually 4. Okay, so the result is 4. Therefore, the parent of 30 is actually the element that has uh, which has index 4, which is 66. So the parent of 30 is, there you are. Okay, so that's how you look for parent. Now, how about you look for the child? Okay, so let's using the formula given, looking for the child or left child. So we want to, let's say, look for the left child. Okay, left child of, let's say, 87. Okay, so the index of 87 is actually, what's the index of 87? It's 1. Okay, so using the formula, you have there 2 times the value, or substitute the value of I, which is 1, okay, plus 1, which is 3. Okay, 2 times 1 is 1 plus 1, 3. So the index, the parent of 87 is, or the, sorry, the left child of 87 is the element which has an index of 3. So let's look for that in our binary tree. We have here 87. The left child is 32. Okay, so this is the left child. Let's look for in our array. You have here the left child of 87 is the uh, okay, the index which has 32. So there you are. Therefore the left child of 87 is the this one, no, 32. So you can see in our binary heap have there 32. Okay, that's to prove, no? So how about in the right child? If we are going to look for the value of the right child, let's say right child of 87. Okay, so the value of index or the index of 87 is 1. And then we have here, let's substitute the value. So we have 2 times the value of uh, the index value of 87 is 1, plus 1 is equal to 3. Okay, so sorry, sorry. The index value, yeah, tama. Okay, so we have 3. So, but we use the formula, right? This one, plus 2 times 1, which is 4. 2 times 1, which is 2, plus 2, nag-advance ko, is equal to 4. Sorry. Sorry. So, again, going back, the index value of 87 is 1. And actually see it here. And then we use the formula in looking for the right child, 2i plus 2. So you substitute the value of I into the uh, by the value of the index value of 87, which is 1. So 2 times 1 is 2, plus 2 is 4. So the right child, therefore, of 87 is, okay, the right child, if in our binary tree or binary heap, the right child of 87 is 66. Now let's look for using the array. So in the right value of, therefore, 66 is the right value or right child of, this is the left child and this is the right child of 87. Now let's try another one. How about 93? Okay. Okay, let's have 93. Okay, so right child of 93. So the right child of 93 is, so is 42. So let's try if using the formula, if we're able to find the right child of 93. So we have here the index of 2, because when you substitute the value of 2, so 2 times 0 is actually 0, plus 2. So you have the index value of 2. So if you try to look at it in our in our array, the right child of 93 is actually, a right child of 93 is the element which has index of 2, which is 42, and we can prove it using our binary heap or binary heap tree representation. Okay, so that is max heap, okay, using if array based on 1. Now, if there are books uh, that are actually implementing in a different way, it's just actually ang ilang differences is just minimal, only that they use different formula. Okay, so in finding the parent, you use p is equal to I divided by 2. For the looking for the left child, it's 2i, and then for the right child, 2i plus 1. So let's try. Let's say parent of 42. So parent of 42, the I value for 42 is 4. So by the way, this in this in this implementation, you don't put a, okay, when you program this one, you don't put value to 0. So index 0. You skip to that now. So most probably the you start with 1. Okay. So that's it. Now the index value of 42 is index value of 42, sorry. Index value of 42 is actually 3. Okay? So using the formula, I divided by 2, which is 3 divided by 2 is actually 1. So the value that we look for is 1, which is the parent of 42 is 93. So let's try to look at it here. So the parent of 42 is something or an element that has index of, see, That's it, the same. So how about left child? We use the formula 2i. So let's say left child of 93. Okay, left child of 93. Now, left child of 93, the index value of 93 is actually 1. And the formula that is going to be used is 2 times I, which is 1, is equal to 2. 2 times I is 2 times 1 is 2. Therefore, the index that the element that we look or we need to look is the value that has index of 2, which is 87. So as you can see, the left child of 93 is actually 87. Okay, so let's try to look for the right child of 66. So the right child of 66, okay, what's the index of 66? 5. So we use the formula 2, okay, 2 times the value or the index value, which is 5 plus 1. Okay, we have 10 plus 1 is 11. So the right child of 66 is 30. So the right child of 66 is actually 30. So because of the result is the index is 11. So that's it for again max heap and min heap in different ways in a different implementation. So if you're using array, if array base 0, therefore the 0 has the first element or the root. And then if array base on 1, then you skip the index 0. So in terms of min heap, you do the same. Okay. Only that, of course, min heap is the root node or the parent node must be less than to its children. Okay, so that's it for min heap. Okay, now before anything else, we are going to discuss few terminologies of priority queues and binary heap. So we have here percolation or reheapification or reheapify. When we talk about percolation or reheapification, this is a process of moving up either upward or downward towards the nodes of that tree. Okay, so because we most of the time when we are going to construct a binary heap, it's most likely what we most likely we do percolation. Okay, so there are there are two percolations for binary heaps. These are percolation up, so this will happen in upon insertion sometimes, or the other books called it as upkeep or heapify up. Okay. And then we have also percolation down. So percolation down is going to be it's happen on if you are going to delete a node from a binary tree or from your binary heap or from your PQ, and it's also known as down heap or uh, heapify down. Okay, so let's now insert a node. So how do we insert a node to a to a binary heap? So in terms of insertion or inserting node to a binary heap, you will have to take note that, okay, again, if this since this is like a max heap, this is max heap presentation. This is max heap. Okay. So again, the property is it should be a complete binary tree, and then the other property must be it follows the heap property order. So heap property order. So what's heap property order? It depends if you're using max heap. The property order for max heap is all nodes or all parent nodes must be greater than or equal to its children. Okay? So that is if you're using max heap. All right. So let's say we are going to insert 15. Okay. So let's say we are going to insert 15. All right. So if you're going to insert 15 as a node, this will be inserted. So the the insertion happens, it should be placed at the to make it complete binary tree, because that's the property, that's the first property of a max heap. It should be placed it right here. So let's say we have here 15. Okay. So now we have here the node 15. Now this is there is a you will need to compare the the recent the recently inserted node to its parent. So if it is actually less than if it's depending of what we are going to achieve, let's say it's this is massive, right? So if you'll need to compare this 15. If it's greater than its parent, it has to it has to there should be a swapping, which is called percolation app. So since 15 is actually less than two, like the its parent, therefore they are actually in order. So that's the heap property. Okay. So we are going to follow this one. So we have 50. Let's put it here na lang. We have 50, 34, and we have 20, we have 16, and we have 15, and we have here 32, and then we have here 10. So this is now our uh, binary heap after inserting node 15. Now, let's say we are going to insert, okay? Let's say we are going to insert, let's say 40, okay? So if we're going to insert 40 in our node, or in our tree, it should be placed. So using the recently binary heap construction, or the constructed binary heap, we are going to insert in the next level order of in after that it's actually the child of 32, which is, let's say, 40. Okay. So now, since, okay, you will need to do the percolation. So there is a percolation that is going to happen. So you'll need to percolate the 40, or swap, I mean compare 40 as a child to its parent. So is 40 greater than 32? That's actually true. Okay. So in a program, it should be swapped. So you swap 32 and 40. So I will not need to swap here, because it would be difficult for me to, erase our tree. So let's assume that it is now swapped. So the key is 40. So 40 is 40 greater than 34. So we have here 40. So 40 is greater than 34. So that's actually true. Therefore, you have here the 40. So after inserting 40, your node now, or your binary heap, would be, okay, I mean, by the way, it has to continue. By the way, it has to continue uh, comparing. So 40, is 40 greater than 50? So it's actually false. Therefore, it stops from there. So we'll have a binary heap here, like 50 will remain as parent node. 40 will be the child of 50, or left child of 50. And then you have here um you have here 34, and then you have here 32, and then 40 would have like 10. Okay. So uh that is now the modified binary tree, or the updated binary tree of our binary heap, rather, of our the recent or constructed binary heap after inserting 40. So you have here, of course, 20, 16, and then you have 15. Okay. So next is, let's say we are going to insert more. So let's say we are going to insert, let's say 45. So based on our, this is now the recently constructed by a binary heap. So let's say we are going to insert 45. So insert 45. So when you insert 45, it should be the right, it should be placed at the depth, no? Sa parang pinaka deepest, basta level order. I-follow na to ang level order na pag-insert, which is here, we insert the node 45. So there is, you will, when you compare 45 and 34, there is percolation happens or swapping. Okay, so we have here, I mean, this process, what we call percolation. So we compare 45 to 34. Is it greater than 34? That's true. Is 45 greater than 40? That's true. So you will need to compare again it to parents. So you'll have here, is 45 is okay, 45 is greater than 50. That's actually false. So since it's false, okay, it will stop from here. So therefore, the our binary heap would be now 50, 45, and then you have here 40, okay, then you have here 10, and you have here this this is 45, si 40 and 34, na-swap na si Tere, and then you have here 32, okay? Have here 20, 16, and 15. So that is now the the recent your binary heap or the updated binary heap in your binary tree. Okay? So, so 50, 45, 40, 10, 32, and 34. Okay, now how about if we insert another? Okay, so let's say insert 50, let's say more than its root node. Let's say we have 55. Okay, so insert 55. So when we insert 55, it should be placed right here. Okay, so what you will do is that you do the percolation process, which is you compare first the child to its parent. So is 55 greater than 10? That's true. So we have here the 55. Is 55 greater than 45? You have here, that's actually true. So you have here 55 initially, swap siya. And then you have here 55 greater than 50. That's actually true. Therefore, you swap 50 and 45. So with that, it's just a matter of preference. It depends to you, no? If every time you do the percolation or you do the process of percolating it, i-swap nimo, it depends upon sa imong preference. So para di mo malibog, you can actually do that. But again, you will uh, most likely you will erase more, parang daghan kay mong erasures. But again, if you're used into it, you can actually easily trace it. So right here, this is now our final, after inserting 55. So you have here 55 now would be your uh, root node, followed by, so swap naman na si 50 and 55. And then after swapping it, so si ang nag-swap right here is si 55, and you have here 45. Yeah, so we have here 45, and then uh 10 and 55 earlier kay nag-swap. Okay. So then you have here 40, and then you have here 32 and 34. Okay. So, and then of course on your right sub tree, you will have the same 20, 16, and 15. So again, if you are going to insert another node, it should be inserted here and you do the percolation. Okay, next naman is if after all the levels here are already completely filled on the left subtree, you will now then uh, fill with the nodes. Every time you insert a node, you are going to fill all the nodes in the right subtree. Okay, so that they will be complete. Okay, complete binary tree. Okay, because again, it should be number one, complete binary tree, and you should follow the heap property order. So if we try to look at it in our on every let's have our so we will check our binary heap if it's actually parang it it does not violate the heap property order. So we have 55. Is it greater than its children? Yes. Is 50 greater than its children? Yes. Is 50 greater than its children? Yes. 40 rather. Is 45 greater than the child? Its child, which is 10? Yes. So we can also check that one here. 50 is greater. Where is it? After inserting 15 right now, so anyway there's no big change here, so dito sa kaning sunod, which is after we insert 40. This is now the updated value, by the way. So when you insert 40 successfully, is 50 greater than its children? So 45 and 20. So is 45 greater than its children? 40 and 10, yes. Is 40 greater than its children? 32 and 30. That's it. The heap property order is followed. So that's how you insert data or element to your binary heap. Okay, now let's talk about deletion. So how about the deletion property? I mean deletion algorithm. So in deletion, all you need to do is the the algorithm that is going to be followed is the same. It should be complete binary tree, or I mean your tree should be in a complete binary tree. And then secondly, the heap property. So and then every time you delete your every time you delete a max heap, this is max heap, right? So delete heap max heap deletion. So it should be uh, you can actually delete a certain node, but normally when we do a deletion in maxheap, it should be always the root should be deleted. So why? Because that is where we can implement priority queue. Okay, so the highest priority. So should the highest value that is going to be deleted is okay, in this case, because we are actually implementing max heap, therefore 93 is, or the root node should always be deleted first, because again, this is to this is to implement priority queue. So now let's go now with the process of deletion. So if we are going to delete 93, let's say delete we delete 93. Okay. So when we delete 93, you will have to you will have to swap the value. You will have to swap the value of uh, which one is the in terms of the level order now, which one is actually it has or is the last inserted element, so this one. Okay, so you will need to swap 30 and 93. Oh, and then or you can simply delete 93 and then replace it with 30. So in this case, this is now this is the tree or the binary heap now. So 30, 42, 26, you have 12, and then you have here 87, it's like 32, this is 66, and then this is 28, this is 19, and 51. Okay. So, in this ano naman sa deletion is you are going to swap, okay? So you will need to perform the what we call percolation down. Okay? So in the percolation down, you will need to first compare the children to its parent. Okay? But before you will compare the parent to the children to its parent, you will need to compare first which one is the greatest. So example, which of this parent, okay, which of these children rather is the greatest or has the greatest value? So 80, 87. So therefore, you will need to swap 87 and 30. So therefore, 30, this will be you have here 87 and you will have here 30. Okay. So 87 and 30 will be swapped. Okay, that's percolation down. Now, another is you will need to compare the children of 30. So which one is the which one is the greatest, or which one is greater? We have 66. Therefore, you will need to swap 66 and 30. So you'll have here 30 and you have here 66. Okay, so this time you will since 30 has only one child, therefore automatic 51 will be compared to 30. So is 51 greater than 30? Or I mean, siyempre kailangan niya i ano ang order that all its node must be greater than its child. So since dili sila in order, therefore 30 and 51 will be swapped. So you have 51 here and then here 30. That's a lot of swap. Oh, what is now your final heap? So here, uh, 87, okay? Next, followed by 66, 42. So dili matandog ang 40, right sub 3. And then you have here 66, you have here 32. And then right here, you have 51, tama? So 51, and then you have left sub 3 of 30. Okay? Okay, and then in your in the child or children of 32 is 28 and 10. So you have here 93 is already deleted. 93 can actually place it. I mean, you can actually place 93 anywhere if you want. So 93 is successfully deleted. Now let's check the order of our. Is it complete binary tree? Yes. Next question, is it following the order of max heap, which is dapat greater ang ato ang parent kaysa sa iyang children. So let's check. So 87 is greater than its children. So 66 it's greater than its children. Greater si 51 kay 30, si 32 kay 28 and 9. Okay? So that's it. That's how you delete a node in Maxit. Now, if you are going to delete another node, 87 will be deleted. So let's say 87 will be deleted. So if 87 will be deleted, okay, so you will need to swap this one, 30, okay? So swap nimo si 30 and, or I mean, i-replace nimo si 30 to its parent node. Wala na ni siya dire. So we are going to perform percolation down. So right here, compare nimo si parent, child or children kung asa ang greater. Since 66 is greater than 42, so swap si 30 is swap nimo kay 66. So you have here 30 and you have here 66. Okay, so compare the children. Which one is the greater? Which one is greater? So 51. So 51 is 51 greater than 30? Yes. So that means you will need to swap 51 and 30. So dire na si 51, dire na si 30. So that's it. And then you have here your binary heap would be 66. Okay, so you have your 51 and then followed by the right child, which is 30, your 32, your 28, and 19. And then 66 right here will be, will have 42 as its right child, and then 16 left child, and walay changes. So let's check is it complete binary tree? Yes. Is it uh, following the heap order property? Yes, 66 is greater than its children, 51 is greater than its children, and 32 is greater than its children. So this is like 28, no? So that's it. Now, if you will now remove the delete again or perform another deletion, so we will delete 66. So when you delete 66 again, so you will have to asa man ang deepest node, so you have here 28 and 19. So but since the last inserted is 19, so therefore 19 will swap here. Okay, I will be swapped in our node or in the parent node. So you have here 19, and then as you can see, kinsa may greater nila 51 and 42 as the children of 19. So since 51, therefore you'll have here 19, and then you have here 51. So which one is greater? So 32. Therefore, what you will need to do is swap 19 and 30. Okay, so this time, compare the children. So 28. So is 28 greater than 19? Yes. Therefore, you will need to swap 28 to, so, why 19? 28 happens. You have 19. Wala naman is 19, no? Sorry, sorry. So you have 28 and then 19 and 28 will be swapped. Therefore, your node now will be, ano man tadapit dire. So we have here data 51, and then you have here 32, 42, 16, 12, and then you have here under your 32, you have 32, 30, okay? And then under your 32 is 28. And so that's it. All right. So is it by a complete binary tree? Yes. Is it uh, following the heap order property? 51 greater sa iyang parent, 32 greater sa iyang parent, as children rather. So 51 greater sa iyang children, 32 greater sa iyang children. So let's delete one more. So let's say we are going to delete one more. So when 51 is deleted, 51, so this will be swapped with the value of 19. So yeah, therefore, right here, it's not always the case na kung asa ka nag-delete, basin inyo mo na inyong idea, if asa ka nag-delete, dito ka mag-add to percolation down. So again, since 19 is going to replace the value of 51, okay, the algorithm that is going to be followed is you compare the nodes, okay, the children nodes. So which one is the greater or which one is greatest or greater, you will need to swap the value to with 19. So since 42 is greater than 32, therefore, dito mag-percolation down. So you have here 42 and you have here 19. So now, which one is greater sa children sa 19? You have 16. Therefore, si 16, ay, okay, there's no need, sorry. Sorry for that. There's no need to, there's no need to delete kasi there's no need to swap kasi it's already in order. Okay. So, ganahan ko calculation down. So uh, pag compare nimo siya the highest value or the max value is 16, pag compare niya sa iyang child is as a parent is since mas greater si parent so in order na siya or it does not violate the uh, binary heap property order. So therefore ato ang heap karon would be 42, 19, 16, and 21, and then you have here 32, and then 30, and check na to. Is it complete binary tree? Yes. Is it is it following the heap order property? So let's check. Is 42 greater than its children? Yes. Is 32 greater than its children? Yes. Is 19 greater than its children? Yes, tanan. So therefore, our deletion is we we perform the correct deletion. So if you keep on deleting and deleting, it's you will have to always note that the parent node. No? So when you keep on deleting, the parent node is always greater than to its children. Okay? Because it's we use the max heap. We implemented max heap binary heap. Okay? Or we implemented max heap property. So it's always going to be the max value. So again and again, every time you delete, you will always delete the root, and then since ang root mauna siya ang max heap, so ma-delete na po siya. Next is the another node which is actually the max value. So in that sense, okay, we if we keep on deleting or removing nodes to our heap, this would arrive a this would arrive descending order. Okay, descending order, which is actually a sort. Tawag nato saya is heap sort. So see, this priority queue and binary heap can may arrive a lot of actually daghan kay siya pwede na ma-arrive nimo. So aside from you are able to do priority queue at the same time find a max hit, you are also able to arrive with a sorting algorithm. So in your data structures and algorithm, I guess you can actually add this one, heap sort in your sorting technique. Okay, so that is for max heap descending. And then for min heap naman, since sa min heap is all parent nodes must be less than to its children, therefore you are able to arrive ascending order in min heap. Okay, so that's it for the deletion of node. Okay, so now let's have building a heap, but before that, I'm gonna be let's have a review on the you're going to find or search to perform search operation in binary heap, again, you either follow this formula depending on what is asked to you, no? Or depending on what you are going to follow, is if it's array based on 0 or array based on 1. And then, so later on, we are going to perform a build, how to construct or build a heap given that there are pre-given nodes already. Okay, so what if there are pre-given nodes already? How are we going to build a heap out of it? Okay, so I'm going to discuss that one in the next session. So to conclude, the if you're going to use array-based representation of a complete binary tree, there is an easy way to determine the parent and the children of any node without following left and right child or pointers, just like what we did in binary trees and binary search tree data structures when we implement it using linked list. And then consequently, in this case, it is sufficient to store the data items on. So because when you get to store, it is I mean it could be zero of n or constant value of one to zero of log n. And then because you use indices, it would be easier for us to perform searching by just using formula. Okay, so thank you guys for watching this video and have a great day. See you guys next in the next session. Okay, bye bye.